Okay, let's have a very quick introduction to the notion of vector space and vector subspace, also called linear space. Okay, so this is really what we're going to do during semester two, but as I told you, I just want to introduce those ideas on things that we can easily manipulate, like matrices. Okay, so just to have a glimpse of what we're going to do during semester two, we're going to have, so that might be chapter 3, may be another number, uh, some big stuff about what's called vector space and linear maps. All right, and so let's just have a look at that definition, that first definition. A vector space, and actually that was the Wikipedia definition, is a collection of objects called vectors, which may be added together and multiplied by numbers called scalars. Okay, so it looks, well, another one that now that you know what is a linear combination, it's some collection of vectors where the linear combinations still belong to the same collection. Okay, so more about this in a while. Some examples are C and in general Rn and Cn, the set of polynomials, the set of matrices, the set of all functions. Well, there are many examples, and you see these are some very general examples. But we're going to talk mostly about Rn. Okay, and why? Because it's easy to work with that, and that's we can even visualize what it's doing in R2 and R3. Let's have a quick look at the Wikipedia page. So you see that drawing on the right, you've got what it means to add two vectors, all right? So you already know this, to add two vectors, multiply one of them by a scalar number. So if you are in the plane, or even if you're not in the plane, you know that those combinations, the set of all combinations define a plane, yeah, as long as your two vectors are not collinear. So this is a very we don't need to go over through this now. What there is just one drawing I want to show you. It comes later on. Okay, this is it. In R3, okay, R3 is also going to be a vector space. Well, basically, why are R2, R3, and Rn vector spaces? Because you take a vector in R2, multiply it by a scalar number, you still have a vector in R2. And you take two vectors in R2, add them together, you get a vector in R2. Same thing for R3 and same thing for Rn. All linear combinations stay in the same space. What happens in a vector space stays in a vector space. Okay, so you've got okay, the idea of a vector space, we have this collection and we know how to add things and how to multiply them by a scalar number. And then we will talk about subspaces, meaning subsets of this collection where you still have the same property that the linear combinations of items in that subset are staying in that subset. So that could be a line in a plane in a plane, or a line in R3. That could be a plane in R3, but not any plane, not any line. We're going to have a look at that. Okay, so let's go back to my writing. Okay, so well, maybe we don't need a very rigorous definition, but V is a vector space if for all, let's call this V1, V2 in V. So these are called vectors. So that's not really a definition, that's more like a property. And for all V1, V2 in V, and for any lambda that belong to R, we have that lambda V1 plus V2 belongs to V. Linear combinations stay where they are, in the set where the items belong to. Okay, so that's what we're going to work a lot on during second semester. For the moment, we're only going to work on R2, R3, Rn. Okay, take a vector in R3, let's say x1, y1, z1, take another one, x2, y2, z2. You know how to multiply one vector by a real number, so lambda x1 And you know, so that first operation is called the outer multiplication. So you get lambda x1, lambda y1, lambda z1. That is still something that belongs to R3. That is still a vector in R3. And you can add it with another vector in R3. That's giving you the vector lambda x1 plus x2. The components are lambda y1 plus y2, lambda z1 plus z2. That is still an element of R3. Okay, so that is a vector space, and one of the first property that we can see is that the zero element belongs to your any vector space. Okay, why is that? It means that if you are allowed it to take linear combination of vectors, for instance, you can add vector and add -1 times the same vector, okay, and that's giving you 0. So of course the some 0 belongs to it, okay, or you can see that as multiplying a vector by the scalar 0. Okay, this is the capital V, these are small, and that should give you the 0 vector of V. Right. So in any case, when you've got a vector space, the 0 belongs to that vector space. That's more that seems quite obvious when you are in R2 and R3. But when we're going to talk about subspaces, linear subspaces, so vector subspace, it's a subset of a vector space such that any linear combination of elements of that subset belong to stay in that subset. How can we write this? So a subset, let's call that U of a vector space V, is such that for any V1, V2 that belong to U, for any lambda that belong to R, then lambda V1 plus V2 stays in that subset. Okay, so example, let's take a line that goes through the origin. Okay, so I know you've talked about this last year yet. Let's talk about this line. This line can be written as actually is just the collection of all vectors. Let's say that this is a direction vector. This is anything that can be written as a parameter k times my vector A. Okay, and we even have this notation. Maybe you haven't seen that last year, but let's say that this line is in the span of the vector A, meaning anything that can be written as a constant mu k, whatever your constant is, times that vector A, it belongs to my line. Okay, so I can take -1 times A, that's going to be here. That still belongs to my O line. I can take 2A and add -10A. That's still going to be something that belongs to my line. Okay, so that line is a vector subset, subspace, sorry, of R2. That's a subspace, linear subspace of R2. And actually, it's very quick to see all the linear subspaces of R2. What are all the linear subspaces of R2? So any line, we've just seen that, any line that goes through 0, through the origin. Why? Because we said, well, I need to be able to take 0 times A, and it still belongs to my space, because that's a trivial linear combination of my vector A. Okay, and if ever you wanted to take a line that doesn't go through the origin, let's say it has the same even with the same direction vector, well, it doesn't matter, it could have any direction vector. The thing is that it doesn't go through the origin, so you can describe this as, the parametric equation of this thing could be described by take some point A, maybe that intercept here, and it's going to be T times A, right? So that would be the parametric description of that line. If you take two elements on that line, let's take let me choose a nice color. Let's take one element here. That gives you, this is the vector corresponding to that point, that vector OM1. And if you take another vector, another point on that line, that is the vector OM2, you have that OM1 plus OM2 does not belong to this line. Okay, it's not going to be giving you some point. Well, it's just giving you that OM1 plus OM2 gives you that point that does not belong to the line L2. Okay, so to sum up, any line that goes through the origin is going to be a linear subspace. I don't know why this is all blurry suddenly. Is going to be a linear subspace of your sorry, let me pause that. Better. So any line that goes through the origin is going to be a linear subspace of R2, but if it doesn't go through the origin, it's not going to be a linear subspace, okay? What are the other linear subspaces of R2? So I took combinations of one single vector. I've got two more trivial subspaces. One which is just 0, okay? That's a linear subspace. It just contains the 0 vector. Any linear combination of the 0 vector is just going to be the 0 vector, so it's still inside. That's just a trivial one. And you've got also now, so I've got 0 vector, I've got combination of one non-zero vector. Next thing I guess you see is that we can take combinations of two vectors, okay? And so two vectors that don't go through, that are not in the same direction, so not on the same line. So if I take anything, let me use, I don't know, let's use red. If I take anything like this, so let's say my vector A and my vector B doesn't have, it looks, well, my drawing is maybe not the best one because they look perpendicular, but they don't have to be perpendicular. You know that as long as they are not on the same line, I can describe any linear combination of A and B are just going to be any point in the plane. So if I take linear combinations of any two vector, that's just going to be R2. Okay, so linear subspaces of R2, two are nearly cheating, like the 0, 0 is just a single point, the R2 is just the whole space, and the real strictly space of R2 is going to be any line that go through 0, 0. We can do the same thing in R3. So in R3, obviously R3 is a vector space. So we already said that. You can add and multiply by a scalar vectors, and that's just going to be a vector in R3. So if that belongs to R3, that belongs to R3, and that belongs to R, you still get things in R3, so linear combinations belong to them. What are the subspaces, the vector subspaces we have in R3? Well, I shouldn't draw a plane. I should try to draw my three axes. So X, Y, and Z. Okay, so maybe we can begin by the trivial ones. So trivial linear subspaces of R3. So the trivial one, again, the 0, 0, 0 element. If I keep it alone, that can be a vector space, all right? Of course, R3 is a vector space. And then what do we have? Again, anything that would be on any line that goes through the origin. So let's say it has some direction vector. So any line going through the origin. So that could be described as the span of vector A. Anything can be written, so it's just notation that I've introduced, but we're not going to use it a lot during that semester, but well, we're going to use it a bit during that semester, but a lot during the next semester. It just means that set is the set of all linear combinations. So inside of the brackets that are indicated by the span, I have vectors, and then that describes the all linear combinations of A in that case. So anything that are going to be written K times A with K in R. Okay, anything that is collinear to A. All right, so that is a linear subspace that is spanned by one single vector. Next thing is, I guess you see, we can take something that would be spanned by two vectors. So if I take two vectors, let's say A and B, and with A and B non-collinear, okay, well, what am I going to get? So let's say you've got your vector A, your vector B, then what do we get? We get something like the plane described by those two vectors, okay, the infinite plane described by those vectors, okay, and again, it has to go through the origin, so passing through the 0, 0, 0. Again, for the same idea, I want to be able to make 0 times my vector and still be in that plane. I want to be able to add one vector of this set and subtract it itself so that I get the 0. So the 0 must belong to it. So any plane that goes through 0, if your plane doesn't go through the 0, the linear combinations of elements of that plane are not going to stay in that plane. Whereas if it goes through 0, it's going to stay in that plane. Okay. What else can I say about that? So infinite plane described by those two vectors as long as they are not collinear, and that has to go through 0. Okay, so this is the next kind of vector of subspaces that we can have in R3. Well, these are the only vector subspaces that we have in R3, but of course you've got an infinity of planes that are going to satisfy this, okay, and as well as you've got an infinity of lines that are going to satisfy that, okay. And very quickly you can see that the intersection of two linear subspaces is still going to be a subspace. The union of two linear subspaces is not going to be a subspace, but well, we'll see that more clearly during semester 2. Okay, so that was just a broad overview of that. What about, as I said, we are going to talk about Rn this semester. What about the linear subspaces? Well, you can have the 0, of course, you can have the Rn, and anything that would be spanned by 1, 2, 3, etc., up to n vectors. Okay, as long as they are linearly independent, but we're going to talk more about that later. Okay,